Hello, and welcome to FODES, the Future of Design and Engineering Software podcast. My name is Rupinder Tara. On this show, we will have guests that will discuss tools and technology that engineers will find interesting and useful. Today's guest is Gustavo Novarro, founder of Divergence AI. Gustavo has left his native Chile to come to the Bay Area to give engineers a helping hand with AI. By this time, you might be thinking, isn't everybody? But Gustavo is not some opportunist jumping on the AI wave. He has a PhD from U Davis in mathematics, and his knowledge of RF design is a mile deep. So why should you pay attention? Because what Gustavo is doing with AI and RF, adding a co-pilot to Ansys HFSS, could serve as a model for all sorts of simulation. Hi, Gustavo.
Hi, Rupinder. How are you?
Uh,
Very nice
and,
to meet you.
and
How's it
welcome to
going?
the show.
Thank you so much. I'm very
Yeah,
excited to be here.
yeah, I think I wouldn't say neighbors, but we're reasonably close by. You live in San Leandro?
Yeah, that's right.
I'm in Marin County, so right across
Ah,
the
okay,
bay
okay.
from you. Yeah.
I go surfing in Marin County very often. So,
Oh, you're a surfer.
well, a little bit, yeah.
A little bit. Yeah, yeah. I was looking up a little bit of your background, and you're from Chile. Uh,
Yeah. I grew up in Santiago, which is like the
uh,
capital city,
yeah.
and La Serena, which is maybe like a coastal town, if you imagine. Chile is like California, but upside down, right? We both
Upside down
kind of
California,
big,
and
yeah.
really, really long, right? Really
Yeah,
stretched
exactly.
out. Yeah, a
Yeah.
lot like California. I think you share a lot of probably the surf, but also, unfortunately, the earthquakes, right?
Oh yeah. Oh yeah.
I think the worst earthquake ever recorded was in Chile, one of the worst.
Yeah, my wife says that I'm a earthquake snob because I don't flinch for anything above a five, you know. Anything below a five, I was like, oh, that's just a little tremor, you know.
We had to get used to that ourselves. My wife's from Philadelphia, so she
Ah,
knew about earthquakes, but I'm from India. Right, right. And India up in the Himalayas is a huge seismic zone, like
mhm.
also one of the biggest in the world. So I'm kind of an earthquake snob myself.
Yeah, exactly.
I see you have a PhD from the UC Davis.
Mhm.
And do you find that people stop talking to you after they hear that?
The classic response is, oof, I hated mathematics when I was growing up. That's a classic one. And I was like, well, tell me more things that you love so I can say that I hate them too. No,
Yeah.
yeah.
How
I
about pizza? Why don't you?
Yeah, exactly. You love pizza? I hate pizza. No.
I hate
I,
pizza.
I always try to use the opportunity to convince them that mathematics is kind of beautiful. That I think that they have been kind of misled by the typical mathematics propaganda of school, you know. I try to tell
Yeah, yeah.
them,
You don't seem like the kind of person that would scare me as a math instructor. So what examples do you use to make them to
oh,
convince them that
well,
math is fun?
my classic example is that what you learn in school is people tell you that you're learning how to paint, for example. And you're like,
Yeah.
oh, I'm painting. And yes, you're painting a fence, right? And you're painting a fence and it's white and everything else. And you practice a stroke and you learn about, moving the brush up and down. But
Yeah.
would you call that art? No, right? Like you don't really feel it doesn't feel like art. Therefore, you shouldn't call it art. So you shouldn't call it mathematics either, right? So what we're talking about in math, you're thinking about Picasso or like Michelangelo. That's really painting. That's really art. And so that analogy should reflect into what they're thinking. Like, oh, maybe I didn't learn math. What I learned is maybe some techniques to do some calculations, but the beautiful part of it, I didn't really get to explore. And that's the analogy that I kind of tell them. There's a beautiful world out there of like geometry and proofs and the exploration of the physical world through mathematics that I think they're missing out. So that's my typical approach, and hopefully I get them hooked.
Does, does that work? I think I think my wife was impressed enough that I was an engineer without having to learn what engineering really was. So
Yeah, yeah.
how'd you ensnare your wife or is she a mathematician like you?
No, she's not a mathematician. I ensnared her with the same thing. She was like, "Wow, that's such a romantic view." Now, of course, we've been together for more than 10 years, and so she knows that that is hard and you have to think a lot. And so she's not so keen to study. But at the beginning, she was super. She bought it all. So we are.
I imagine intimidated, right? Because that's not
Mm, No, I would say that she's very smart on her own way. She's a PA, like a physician assistant. She's very
okay.
scientific herself.
Right.
She's also very funny, so she keeps me in check. So she's never like, "Oh, my husband."
Interesting.
Yeah.
I promise we'll get back to engineering
Oh.
soon. So my wife is an English major.
Mm-hmm.
I'm an engineering major. So it was a complementary thing, right? Now your wife is a physician's assistant, so she studied medicine.
Mm-hmm.
Do you have this argument all the time? What's harder to learn,
Mm.
medicine or engineering or mathematics in your case, right? What do you have this argument?
Early on, I think we had this argument,
Yeah.
more, but because, for example, Jesse has a profound admiration for medical doctors, for example, right?
Okay.
Because their job is very serious. And in a way, my job, I chose almost specifically for its distance from the real world. Although it turned out in the end that it was not the case. But when I was young, I was
Yeah.
thinking like there's this mathematician called Hardy, this British mathematician, and he would be
Uh-huh.
like, he would abhor if his mathematics were used for something useful. He would do everything for the sake of just intellectual pursuits. And I was the same. I was like, I don't care if this is useful at all. And so this big stark difference between why she does what she does, which is to be as helpful as possible, as practical as helpful as possible, and why I do what I do, which is for like the intellectual pursuit, the beauty of it all. Like even if it's not useful, I would still love to do it. And I think that was our main challenge, not in terms of difficulty. Of course, medicine is hard, takes a lot of years, and math is also well known to be hard. So there was not like that difference, but how useful it's going to end up being.
Useful. Yes, right.
Mm.
So my daughter went into nursing. I couldn't talk her into going into engineering.
Engineering.
I was very unsuccessful with it. Convincing any of my children, either of my children to go into engineering. So she studied nursing. You know how I put her in her place?
How
I,
do you do it?
I said, 'cause she's always trying to tell me how important her job is. I said,
Mhm.
I can kill thousands of people at a time. You can only kill one.
Yeah, I mean exactly. Our impact is measured in the hundreds of years, right?
Yes, correct,
Um,
correct.
yeah,
Okay.
I have a young son, so any tips to convince him to become a mathematician or an engineer, I'll be happy to
Oh, yeah, yeah, yeah.
to
So
learn.
I'll give you some advice because you don't do what I did. I'll give you a cautionary tale. I
Hmm.
took my son to my office with me,
Hmm.
again, trying to impress him with engineering. Look, son, look what I can do. Look, I
Hmm.
specialize in computer-aided design. Watch this, son. And he's sitting he's watching for a little while. Eventually, he just goes and sits in the corner of my room and unimpressed, totally unimpressed. Then he says to me afterwards, he said, Dad, this is what I want to do for the rest of my life is just, and he makes a motion of, pecking at a computer all day. So he,
He was
he
making
became
fun
a
of you.
musician and, and, and,
Ah,
and then, then you know what happened? He ends
mhm.
up using a computer all the
Yeah,
time
yeah, yeah.
because
For composing, yeah, yeah.
I do want to hear about what you're doing. And
Mhm.
it's very impressive. I found a little bit about it. Now, you may have to talk down to me. I'm just a
No,
mechanical
no,
engineer, right?
no,
So
no. Oh, happy to explain anything
okay.
actually.
Let's give you my background so you know what level to talk to. Tell me what company does. So Divergence AI is really narrowly focused on, correct me if I'm wrong, on HFSS. I barely know how to spell it, right?
No, no, correct.
HFSS, which is a application in Ansys for
Mhm.
antenna beams, correct?
Yeah.
Antenna wave
So
propagation, right?
yeah, the way that
So
I
what does
describe
your
it,
software do that helps with that?
yeah. So we are building an agentic copilot for electromagnetic simulations. So if
Okay.
you're a hardware maker that, let's say, builds a communication device or like a jamming device, like or a radar or well, anyways, a ton of stuff has antennas actually,
Sure.
or RF is called radio frequency systems. Then you probably use one of five most popular software out there in the world, Ansys HFSS, which is high frequency simulation software, being one of them, one of maybe the leading software part of it. And so our Copilot helps you automate your workflows with HFSS. So it's kind of giving the power of coding to engineers that typically don't have the time to actually to dedicate to create automation. So they do most things manually.
Okay. So now I've used Ansys before, but it's the structural stuff. Uh,
Mhm.
but Ansys I find is a very difficult program to use. You have to spend a lot of time. You have to learn its terminology. Uh, you have to almost become an Ansys engineer to become an to you become an FEA engineer. And I imagine it's the same way with
Mhm.
HFSS, correct?
Yeah, that's absolutely right.
Yeah.
The learning curve is very high. So what ends up happening is that companies have their RF teams, the people that build the antenna and RF teams. They are very sophisticated engineers. They have a master's, they have PhDs, and
Mhm.
they are the ones that run the simulations, that build the designs, and yeah, and train other people. So it's a like you say, it's a very sophisticated tool. It requires a lot of expertise.
Yeah.
It's very hard to use. Mhm.
Okay. If I'm using Divergence AI, do I still need to know how to learn how to use HFSS? Is it something that helps me automate the usage of uh, HFSS, or is it something that helps me not learn HFSS all? And I can not have to bother with learning it, right? I can
That's
just get
a
my antenna beam patterns without knowing a shred of H. That's what I'm wishing for, but that's
no, no, that's a great question. So okay, so I'll tell you w- maybe where we are right now and
okay.
maybe what our vision is. I'll say right
Okay.
now, you still have to know what you're doing. And I
Okay.
think engineers like to know what they're doing. I'm an engineer too, like I'm a
Yeah.
mathematician, but I've been a physicist and a mathematical engineer, as they call in Chile. And
Okay.
I've been working with engineers for a long time.
Okay.
And I think we don't want to relinquish control, right? So we want to know what we're
Absolutely.
doing, especially for the hard um, bits of simulation. Like the whole goal, right, of what you're trying to do when you design something in HFSS or in any simulation tool actually, is you want to know how it will behave in the real world, and you want to know that answer as close to reality as possible. And so you need to make sure then that your setup, like your materials, your geometry, like your fabrication tolerances, like you explore all these things to the 98% accuracy aspect, right? And then you
Mhm.
run your simulation and you control the mesh size and you do all these things so that when the results come back, you can tell your boss or you can tell yourself that, listen, now we're going to fabricate it and it's going to perform like this. And I know this for sure to 98% accuracy. If you
Okay.
don't have that confidence, then what is the point? Like, like you're still going to spend time building it and it will fail the test and you have to go back and redesign it and test it again. The whole point of simulation is to skip that. And so on the setup, you still want to be kind of specific and you still want to be careful. And so right now our goal is to, yes, lower the difficulty level. So maybe more junior engineers that are RF trained, maybe masters or they're just graduated, they can still use HFSS. And more than that, are able to automate to create maybe more complex workflows than what they can currently do using our tool. But it will not replace their thinking. And I think that's a fear that a lot of engineers that I talk to express to me, which is that they don't want to be dumbed the tool down. They don't want the tool to be dumbed down. They want it to be, I don't know, maybe like I said, easier to create like automations perhaps,
Mhm.
but they don't want it to replace the thinking. And I obviously don't want that. Don't
I
want
understand. So you're reducing the complexity in its usage, but you still have to know what you're doing.
the
Yeah.
vision for it is for it to be an intelligent co-pilot, right? So
Right.
it can give you suggestions and it can tell you, okay, would you like to set it up like this, for example? Like the rest of your team at your company sets it up like this, and the reason is X. Would you like to do that? And you can say sure, and it will automatically fill in the details if you want to, but you will always have that ability to say no, 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 I don't want it like that for this case. I want it like this, and so on.
Got it. So,
Um,
correct me if I'm wrong. This would be like the senior analyst here who's doing RF a lot and
mhm.
knows HFSS. They would like help with the automations or tell their junior RF engineers, here's how you can use,
Yeah.
use Divergence AI for what you're doing. And by the way, you can do it a lot faster and you can do many more cases. I really love I saw the demo. I really love the natural language interface you have with that because you can tell quite clearly something that would be, I imagine, very difficult to learn the commands to do, like
Mhm.
steer the beam from 0 to 30 degrees
Yes,
and then give me the beam patterns every 10 degrees, something like that.
yeah,
You
yeah.
can tell that in English.
Yeah, and actually that's a great example that you're bringing up, which I have a demo prepared if you want to see it. But
Yeah. Yeah, I
the
would like to. Yeah. Are you
okay,
able to show a demo? That'd be
yeah,
great.
yeah. So should I do the array? Okay, maybe I'll do two projects. One is more like a 5G waveguide project just to
Uh-huh.
see some post-processing capabilities, and then like for plotting, for creating reports. And then we
Okay.
can do one with an antenna array, which is more for people that are building, radars or satellite communications or like 5G wireless communication stuff.
Okay. All
And
right.
we can do that. And then if you want, I can show you a teaser of like our latest stuff that is under development, but only if you want.
Okay. Yeah, please. Yeah.
Only, only
Yeah.
if that. Okay, let me see. Can you see my screen? Okay.
I can see your screen. Yes.
Okay, perfect. And you see on the left hand side, you see the Ansys HFSS software, and on the right hand side, you see our software.
So
And
you get
that's
all
what.
your geometry from Ansys, so it's already created.
Yeah. So this is what we're connecting to an existing project, and you basically want to do automations on top of this project. So this could be something that a designer is building. For example, this
Okay.
little array of these little kind of square elements here that resonate with the waveguide that's underneath.
Okay.
This radiates some kind of like a beam type thing. And yeah, it's built like the engineers might build it, and then they want to do things with the design, whether this is modified for a specific requirement, maybe a resonance frequency, so it's more efficient at one specific frequency, for example, or they
Mhm.
just need to create a report, or like you said, some of the things like plot a beam and maybe move the beam around, sort of kind of stuff. And
Okay.
on the right hand side is our software, and our software maybe I'll make it a little bit bigger for just for a moment. Uh, our software has three components, which is on top is how you load up a file. And this is, oh, I already connected. So you browse the file that I show you back there and you click load, and our our agents can write a little bit of code to connect to the design and extract design context. And this is the key part of our work actually, is to extract the design variables, the ports, the basically everything that is related to the design itself, so that the agents now have this awareness. And they write code on the right-hand side, which is our Jupyter notebook, live notebook view. So every piece of code that the agents write, it gets written into this notebook that therefore the user can then use later on as well. So we believe in giving all the control, like facilitating the work, but then giving it back to the user. So we don't try to hide
Okay.
the code that was generated
So natural language sort of interface on the left,
on
and
the
then
left. Yeah,
on the
exactly.
code that ANSYS can HFSS can understand on the
On
right.
the right, exactly.
Okay.
And results are also on the right. So for example, you can see that when I loaded this file, it says successfully loaded, and this file has three designs, and the summary is that this one, the one SIW is solved, the 0.5G element is not solved, and the two SIW structure is solved, and it has two ports and 25 variables, for example. So now we can start analyzing, and we can just start asking the questions here directly, for example. So
Okay.
when you say, you can ask things like plot the return loss, uh, the return return loss for all active designs. So I'm going to say S11. So this is a classic thing that an engineer might want to know, which is the response of this antenna at different frequencies.
Okay.
So for all solved designs. And so as you mentioned, our agents basically take this natural language request, and they're trained to know what code to write to interact with the design on the right hand side. So right here, you can see that you can look at the execution trace, and it's using a few tools that we have built for them. And I don't know if you can see, but something is going on the UI, which
Hmm.
is
Hmm.
our agents basically are talking to HFSS and writing some code, and the output is coming in here. So you can see this graph right here is the first one. This is the
Okay.
frequency response of the first SAW structure of just the waveguide. And then
Okay.
it
Okay.
asks you, do you need a comparative plot, for example, of the other design? So I'm going to say yes.
Oh, that's
Yeah.
nice. It's interacting with you. It's
Yeah, yeah,
saying,
exactly.
Here's what I've got so far. And you want anything else? You want some changes?" Or does
Yeah.
it sometimes ask for you to refine your question if you don't have something that it understands?
Yeah, exactly. So
Okay.
sometimes it will try, and for
Mhm.
example, it can write code that fails. For example, it says if you ask it, I don't know, plot the radiation pattern, and it turns
Mhm.
out that there is no setup associated to that, and it's going to try to do it, and it's going to fail, and it says, it failed. Maybe it failed because this is not there. Would you like me to give you instructions on how to set it up? And it will kind of help you through that process. So, for example, I'm
It's,
going to say plot the one.
you forgot to model it, you dummy, something like that.
Yeah, exactly. Sometimes it says there is no you are asking for things that have no results yet, and
Yeah.
that definitely happens. Yeah, yeah.
Okay.
So I guess I plot the one for the two SIW design, because I want to see the response of the full with the one with the array. So the agent's gonna take a look in here, and uh, oh, did he plot it already? Oh yeah, it plotted up here. Sorry, it says like you said, it says dummy. I already plotted it. It's up there. Take a look.
I mean,
And,
you taught it to be polite. That's good. Okay. All right.
exactly. And so
Yeah.
you can keep asking questions. So, for example, another thing that
Yeah.
engineers kind of care about is like plot the speed chart, for example. Um, and then our agents also know how to do that. And this allows you to understand um, what is the matching, like how good is your match to the frequency that you're trying to do.
Mhm.
And sometimes when the agents need to think, they create this to-do list. So they has this ability to say, okay, if I'm going to set up a long workflow, maybe I'm going to break it down into pieces and I'm going to attack each piece one by one. So here you go. This is the Smith chart with the impedance for S11 over these frequency ranges. And I think obviously this is very manual still. Like if you were to do it, you would still click. And right now this feels not as a big advantage.
Mhm.
But the advantage goes into saying, okay, maybe I want to create a full report. So you can say, okay, I'm going to say plot S11 for all designs, then plot maybe, okay, there's another Y11 for all. Uh, and then I say, then plot the far field. Then I don't know what else we can do. We can do more stuff, and then plot the beam. Yeah, and
Okay.
plot the beam. Uh, and maybe this is you describing at the beginning of your workflow, like everything you need to be happy, and
Mhm.
just letting it go, letting the agents do their job, and you can go to do some tests on the
Something
bench
else.
or something else, exactly something.
Right. Right.
Um, and so you
Yeah.
can see that you create this to-do list, and as it executes it, you can go be free basically, and you can ask if you can even ask to this to-do list. So you can say notify me, by email,
Hmm.
when this is done.
You could actually run
Yeah,
hundreds of simulations and sequential simulations and
yeah,
just walk away and it would
exactly,
do them all
exactly.
for you.
Yeah, and I think this is where the power of what we're trying to build happens, because normally what an engineer will have to do to build this automation is that they will have to be very good at writing this code right here, this
Mhm.
type of code, which is using the Ansys Python API. And,
Okay.
and that's a very rare skill.
Yeah.
So those people are like unicorns, and I think my co-founder and me are
Oh, yeah, yeah.
have them.
That just scares me looking at that stuff. It's like I can't do that. I
And
don't want us to devote 6 months of my life to learning how to use that
yeah.
code either, right? So I think
Uh,
this is worth its weight in gold, something like this. Tell me how much gold is out there because okay, I don't know much about this specific field,
mhm, mhm.
but it's got to be more than dozens of people who are doing analysis.
Yeah, so we are going after basically the big industries out there. So we're going through aerospace, telecommunications,
Mhm.
consumer electronics, wireless design. So
Oh
this,
yeah, because wouldn't 5G, all the antennas they're making now, really
yeah,
benefit from this sort of simulation and
yeah,
automation?
exactly,
Yeah.
exactly. So
Okay.
our
Okay.
ideal customers on that space are Cisco, for example.
Uh-huh.
On the consumer electronics side, you have Apple, right? How many antennas are in the iPhone 17? I think it's something like 15 antennas,
Exactly,
right?
exactly.
Yeah.
I was just going to ask you about that because one of the problems that I read about in its development was, how the antenna is going to fare if it's across the top or the side. They had to spend a lot of time with that. And I don't think they had your tools, Gustavo, right? I don't think they
Mm.
had. So they were
Yeah,
probably doing it iteratively, one step at a time, trying to figure that out. That was a
yeah.
tough problem for them to solve, where to put the antenna and not have it, not drop the call, but depending on how the phone is oriented, right?
Mhm. Yeah,
So,
yeah, exactly. So radio frequency is all basically
right.
antenna engineering. It's
It's all RF. This applies in several fields, not just RF, but making the
Mhm.
invisible visible
Yes, exactly.
is what
Exactly.
one of the main things about simulation software. Another application I'm thinking of, tell me if your software can help with this or your AI can help with this, is vehicle-to-vehicle communications, which
Yes.
uses I think it is planned on using 5G, but that must have a lot of antennas, right? It's
Mhm.
autonomous driving. They have arrays of antennas. They're all good applications, right?
Yeah, exactly. And so actually this is a great point. You're making all the advertising for me, Rupinder. This is wonderful.
Ah.
So so my goal really is to help engineers. So when
Yeah.
I talk to them, when I talk to RF engineers, I consider them to be the most brilliant engineers, by the way. Sorry to the mechanicals out there. I think they're very
It's
smart
okay. It's
also.
okay. I'm used to it.
But they always say like RF is black magic or is incredibly hard, and I agree.
Yeah.
But it's also very beautiful. So anyways, we can.
It is, but you have a mind that can see things I cannot, right? To me, it's like I can't see it. It's not intuitive. You seem to be able to see it, but better than that, you can explain it and you can even help analyze it. So, yeah,
Mhm.
yeah,
So when I talk to them and I try to think of what problems they have. Obviously, they always complain about simulation time. Simulation time is too much, and there's a lot of companies that are trying to solve that problem with AI. They're building physical models. I think you had NTOP in your
yes,
podcast, and so they're
yes,
they're building super interesting models.
right.
But there is other times, right? That there is a setup that is very manual. There is repetitive tasks. There's like workflows that are not well suited for automation unless you dedicate a ton of time. And these engineers are like very brilliant. They don't have time to do to this dedication. I'm sure they could learn how to code and do it. This is certain, but they don't have the time or they shouldn't dedicate it to this. They should be thinking like higher level product decisions.
Right.
And one of these examples is yeah, you design an antenna in HFSS, for example, and then you want to put it in a car or an airplane. Well, the process of moving it from there to the car, it involves a separate software actually. So you
Hmm.
have to use, let me do a plug for some of my friends here at EMA 3D, for example. They build simulation software that is precisely meant to understand the propagation of the antenna fields on a car and see
Hmm.
how it affects the cables and stuff like that, or into an airplane. And then that workflow is very manual. The engineer has to take the design, export into some file, put it into another thing, run the simulation there, get a report, and then finally understand. Whereas we aim to be that orchestration layer that you tell the agents, hey, do this. Like this is not a heavy thinking process. And the agent say, okay, writes the code, takes the fields, move it to the next file, and now interacts with the other software, gets a report, and send it back to the user. And the user can say, oh, now I see the outcome. Wonderful. That's
Yeah.
really
Yeah.
our goal. So
Yeah.
we
No,
are
that's
working hard to integrate actually with those products.
okay. Okay. That's good. It's great that you're building it on a foundation of tried and trusted simulation software.
Mhm.
Uh, you're just adding a layer of AI on top of it, it seems to me. I'm sorry if am I oversimplifying, but this is much better than other AI tools, which I think were trying to synthesize this simulation.
Mhm.
Like go to the next step in an analysis by similarity to another analysis without using the code whatsoever. And
Yeah.
there was something very scary about that. It's like
Mm.
okay, I understand you can synthesize if it's very similar. For example, you change the wing design a little bit, right?
Yeah. Mhm.
And then yeah, okay, maybe you can extrapolate to that, right? But if you're going to change the wing design a lot,
Mm.
right? If you're going to go from wing body to a, let's say, a box body,
Mhm.
uh, your extrapolation is not going to
Too
work,
much.
right?
Too
It's
much. Yeah.
you still need the code.
Yeah.
You still need the simulation code.
We're going philosophical, Rupinder. This is great. This is wonderful.
Okay.
Before I answer that question, let me just review. So
Yeah.
the outcome is just done. So
Yeah.
basically, the entire list of the two plots basically are here, and the Y11 also plotted here. It wrote all the code, and this is the 3D pattern of the antenna that we just plotted, and then finally a 2D cut of it. The
Oh, good,
beam,
good.
the
So
beam.
all I've seen before is beam patterns, but you can do the full 3D.
Yeah, full 3D also. Yeah, yeah,
Good, good.
exactly.
Okay.
And and the point was that we just left it happen. We didn't have to do anything. You and I just chatted, right? And you suddenly have this report ready to go, which is the goal to release the engineers to do more stuff.
Okay.
But yeah, but so let's go philosophical because I like this question a lot. I posted on LinkedIn about it where I was thinking in my head, I'm a mathematician, right? I studied the algorithms that the solvers use behind the scenes to model the physics.
Hmm.
So is a differential equation that it's an approximation of reality, right? Like the wave equation is an approximation of
Sure.
reality to some degree that is accurate.
Right.
And then we are discretizing it, right? We're discretizing to a mesh, and then we are propagating this discrete values of this differential equation through this mesh, and we iterate it over time. And for all these steps, there are errors, and we accumulate errors along the way. And we are just happy to know that the mathematicians of old and the physicists of old found bounds to maintain this error small enough. Like we discovered that if the mesh is small enough, then our error is small enough. There's a proportionality there. So we're kind of
Hmm.
happy with that. We trust it so much. It has a history of being effective. And so we trust it, right? We
Hmm.
say, oh, finite element has been good for us building bridges and stuff for the last 50 years. And so
Yeah.
we
Yeah.
really, we really, maybe,
We
maybe
like it. We,
more.
we like it.
We like
We
it.
may not like working with it, but we like it, and we know it
Right.
works. It's solid foundation, right?
Yeah.
Don't throw it away. Right?
So I had
Uh,
a philosophical question about the AI models where if you just look at them abstractly and we say, this is just a method, right? Don't
mhm.
forget that it's AI or forget that it's machine learning, whatever. It's just a
Right.
method that it allows you to approximate a function, which is the solution, right? Either the fields, the thermal fields, or the velocity fields, or in the case for NTOP and stuff. Uh, what's the difference? If we eventually have the scientists telling us that the error bounds, and we know that the errors are small in comparison with our distance to the original training data. Like
Mhm.
you said, like if you start with a wing and you take a box wing, maybe the distance from the new data to the original training data is too much, and so the error is going to be big in comparison. But if you're doing modifications that are small in size in comparison with the training data, philosophically, what's the difference? Like
Mhm.
I tend to see these two methods as just methods of solving it.
Yeah.
I don't consider them necessarily bad. Uh,
Right, right. Two
especially-
methods, and you're right. If it's either small time extrapolation or small time interpolation, it can probably work. That works really well with rendering, like
Mhm.
visualization and rendering,
Yeah,
where you can see, oh, this is going to be that color in between these two colors, and
yeah,
this so fill it in. Don't wait like hours for the computer to do the ray tracing. Fill in
yes,
that last little bit.
yeah,
So yeah, and also might work if the model is diverging to a solution.
hmm,
Maybe AI could step in and say, "Oh, the final solution is going to be along this because this is asymptotically approaching that." But
yeah, yeah, yeah,
yeah, but please don't make the big assumptions, right?
exactly.
Don't throw out the engine and expect the car to run.
Yeah. My opinion is that these algorithms, like the AI algorithms for physics, will
Right?
have a very important place
Mm.
to play in this whole orchestration. Of course,
Right?
I'm very biased to think that my orchestration tool will actually help engineers move designs in the right cycles of AI design and
Yeah.
then move them into validation stages with the real algorithm. So
Right.
because if you think about it, like these systems will have some tolerances that are perhaps bigger. Maybe they will give you 70% approximation and 80% approximation of how it will behave in the real world. And perhaps that is good enough early on. And so you might want to trade off the accuracy for speed. And you might want to say, you know what, for this antenna, run it 10 times or for 10 different designs on my AI engine,
Mhm.
give me 80% there, and now send me to a validation stage. And of course, our agents are going to be the one moving this thing around.
Yeah, I hope so. I did notice that your agent is a little bit more interactive than what I'm seeing. I see a few of these products, and most of the time they just spit out an answer. And,
Mm,
you know, sometimes it's good, sometimes it's way off. But at no time do they say something like, wait, I didn't catch that, or you didn't model that. And your software said, okay, you didn't give me that information. Now,
mm,
when you give it to me, I wish AI would be more interactive like
mhm,
that. All AI should just don't just come with me an answer, because if you give me the wrong answer, I will probably not use you again. But if
mhm.
you work with me, right? If you
Yes.
sense where I'm going and maybe I need to give you more information, uh, I love that, right? As an engineer, design engineer, I love that assistance. You know, it help me with the tasks that I have trouble with, but learn from me. Don't just jump to the answer. I saw a ad one time. It was a kind of a joke where there was a sign draped on a building under construction, and they said, "Hey, AI, finish the building." Right? And and the joke was, of course, that AI can't really make buildings,
Yeah.
but there's enough AI right now, especially this prompt to shape
Ah,
uh,
yeah.
software that's trying to do that. And as an engineer, I'm extremely worried
Skeptical. Yeah.
of that happening, right? That people will say, "Oh, that's the AI I want. I don't really need the math. I don't need the structure. I don't need the FEA,"
Yeah.
right? Yeah.
I think that's very interesting. What do I feel about it? That's a great question. So obviously I'm looking at the space. This is important for us. A big problem for RF engineers sometimes is something called defeaturing, which
Yeah.
is
Feature. We have that in the mechanical side too. Like
yeah,
take out the little holes. They won't.
exactly,
Yeah.
because maybe they don't matter for thermal analysis, right? And if
Right.
you were to mesh every single detail, it would be just a ginormous mesh, which means ginormous simulation time, and maybe it doesn't matter. And
Hmm.
you again, as an engineer, you want to know that you're playing that trade-off, right?
Right.
But you need to know. I think that's the key.
Yeah.
And so for us, in our Copilot, what we're seeing in our roadmap is that we want to help engineers actually do the pre-processing. So, for example, if you're putting an antenna on a rocket, this is actually one of our potential customers wants to
Uh-huh.
do this. And we're thinking, okay, well, sometimes they get the rocket from the mechanical team, and it has so many little parts that they are like, forget the rocket, we're gonna draw our own rocket. And they draw a cylinder, and they slap the thing. And the reason for that is, again, to play this trade-off. But that process is so time consuming that they prefer if some AI can take the original shape and simplify it. And so we are working on that right now. Uh, we don't have it right now, but we're trying to work on what we're calling the pre-processing agent. So what I showed you right now was a post-processing agent. The simulation is already run and allows you to extract, results and reports and stuff post-processing. We have also a simulation agent that allows you to run optimizations, parametric sweeps, and it basically monitors the status of your run. If it fails, like you mentioned, or if it's not converging, the agent will
Hmm.
jump in and say stop, or run again, just in case you leave something running overnight, and then you don't want to wake up the next morning to a failed simulation.
Okay.
So basically, a simulation agent is like having a junior engineer just looking, uh,
Yeah. Yeah.
and now we're working on the pre-processing side, and this is maybe some of the things that I was thinking of showing you if you're curious of what we're trying to do.
Yeah. Please, if you have time, I'd love to.
Yeah, yeah,
Yeah.
happy to actually. This is under development, so maybe maybe it will not work right away. So this is running on our development branch. So this is an empty project, and what we're trying to work on is giving the agent the ability to draw some stuff. And this is important because for RF engineers in particular, there are a lot of things that are out of the box, like a patch antenna, for example. This should be easy. A dipole or a horn antenna. These are things that you use for testing things, and you don't want to be importing it all the time or drawing it from scratch all the time. So we want to facilitate that process. So here, I'm giving the agent the ability to create some geometry. So say, for example, let's just ask what types of antennas can you create? And of course, our agent has a list of things that they can do. Let's see what we get.
Yeah. So it's thinking.
It's thinking, yeah. It says I can create a variety of antennas. Okay. A bow tie, right? Something like
Okay.
this.
Uh-huh.
Standard, rounded, and slot, patch antennas, pro-fed, and horn antennas, and helix antennas. So let me know if you like details of which one and what are they for.
Okay.
So maybe we can ask. So okay, so let's just create a microstrip patch antenna with a inset feed. And we have to tell it the frequency because that matters on the size. So
Okay.
at, let's say, Wi-Fi frequency, so gigahertz. We used to build these patch antennas all the time in my old company, where at reach power, because
Hmm.
we were building antenna arrays of this. So you can see that the agent is writing some code and actually is creating the geometry. So if we go back, it added the geometry here right away, and it created the the antenna
Hmm.
out of nothing. And the whole goal is like this used to take, I don't know, an hour for an engineer.
Yeah.
They can just
Yeah.
ask it and get it done. And we're working on creating arrays now. So you can say, give me an array of 5 by 5 of this. Boom, 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 and have it to be reusable. And so, for
Okay.
example,
Now, this was all done by reading all the documentation for the Ansys software,
so
and then
yes, actually, so Ansys has a very good open source library called
okay.
Antenna Toolkit. And
Oh, okay.
what we did is we looked at this and said, okay, this is perfect. Like I started asking RF engineers, do you use the antenna toolkit? Do you use the antenna toolkit? And they're like, no, they build these things from scratch. And I'm like, why do you build it from scratch? And it's because it's hard to use. Like this is literally the only answer. So we're like, let's just make our agent use it instead. So we
Yeah.
integrate it. And this is the same thing that we're doing with this couple of very brilliant engineers from Manitoba University. They built a library to analyze wireless networks, but it's a Python library. So that means that if you want to use it, you need to know how to code. And so you have again this dilemma of RF engineers that if they want to use very advanced
You have to learn
wireless
Python.
analysis, they have to code it in.
Yeah.
So we are collaborating so that we have an agent, which is a wireless agent now.
I love it. I love
And
it.
then
I
we'll
don't want
just
to do the engineering. You do the coding side.
exactly, exactly,
Yeah.
exactly. You do the engineering, exactly. We do the
Yeah.
coding and we give you
Yeah.
this thing back. And so, for example, now it's saying, okay, I make this rectangular microstrip antenna and I use this type of substrate, FR4, which this thickness, this the dimensions were automatically calculated for that resonance frequency. And the setup is ready. So would you like to run a simulation? So let's just say, yeah, yes, please, let's run it. And so great. So our agent should. And you can see that it's happening here. So our HFSS is starting to think and it's loading, is running this analysis. So we didn't really have to do anything. So once this is integrated to our main code,
Right.
you will just be able to set it run and get out of here, and you will have the answer in, I don't know, 5 minutes or so. And little by little, we want to add more power to the
Uh-huh.
processing agent.
Yeah.
So
Yeah.
this is going to take a while. So maybe we can leave it thinking while we talk.
Yeah. I'm going to think selfishly again about
Mhm.
mechanical engineers, right? So, couldn't there be something like this for stress analysis or
Ah,
vibration or thermal, right? Why do I have to? Okay, I used to do that stuff, but
mm.
years ago, but I doubt if I could do it now without having to relearn it, right? So here I am asking for, is there is there a Gustavo in the structural side, right? Is there, or are you
Yes.
gonna, is that the plan? Are you gonna try to do this for other disciplines?
Rupini, you're asking the multi-million dollar question right here. Yeah. Yeah, we want to.
Yeah.
So I fairly new to the Valley, right? I don't
Okay.
have a big track record of companies. And so one of the things that I want to do is I want to make sure that we have a validated go-to-market strategy on a very small niche, like an industry like electromagnetics, where me and my co-founders' expertise can be very useful to sell, to create trust and confidence, right? And we are trying to become Ansys technology partners, for example, which
Uh-huh.
which again will help to get more channels and more traction and more sales. But once we have a traction that is well established, then we definitely want to go cross domain. So go
Okay.
thermal, go mechanical,
Okay.
and
Okay.
have our agents be actually uh, the orchestrator of a much larger workflow where you have mechanical engineers sending jobs to the agents and you'll have passing them to the RF engineers that will send them back to the mechanical engineers for analysis after the RF systems are designed. And then they will go back to some other types of engineers. And all these things, we want to make it easy and we want to make it uh,
Hmm.
uh, uh, but at the same time, we don't want to dumb it down. We want to keep it at high level so that every engineer feels like Iron Man, so they can just send
Yeah.
it
Yeah.
out to their AIs to
Right.
do the tedious work, but they can be thinking the hard part.
Yeah. Yeah. No, it's a brilliant approach. I say genius to anybody who agrees with me. But in this case,
That's genius.
in this case, this is something I really want to happen. So hurry up. So, so I want it to happen in my field, of course, but I really appreciate you spending the time to explain RF to me and antenna design. I really love the fact that you're using engineers' trusted tools and
Mhm.
helping them make them easier to use. And it's starting off with something you know specifically quite well.
I learned a lot from my previous work, so if I can do anything on this podcast to thank them, to thank Chris and Rich Power and Hunter and Varun, the early team. We were just four guys in a garage literally, and I came as a mathematician, designing algorithms and being very abstract, but little by little started doing embedded code and like working on the RF systems and like trying to help with the simulations and soldering literally
Oh
amplifiers
yeah.
to
Uh-huh.
antennas that were blowing up.
Yeah.
Uh, and so I learned just by being close to them. And I really want to create something that will benefit a company like that. And
Hmm.
and the many companies like that are out there in the world.
Hmm. Thank you for coming on. I know you're going to do great things, and I want to keep up with your progress. Thanks again, and
It was
have a good
delightful.
rest of
Thank
the
you.
day. Okay.
Thank you so much. See
Thank you.
you.
Bye-bye.
Thank you for listening to FODES, the Future of Design and Engineering Software show, brought to you by Eng Technica. I hope you have learned of a new application or technology that will help you with your job. If you have an application you think would be of interest to other engineers, please let me know by emailing me at rupinder@engtechnica.com or message me on LinkedIn.